And now in this lecture we find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and one square. The radius of the small circle is equal to 1 unit. The side length of the square is equal to 3 units. And our mission is to find out the radius of this big circle. So, first of all, we will define the vertex here as A. We define this vertex as B. We define this vertex as C. We define the point of tendency of tangent BC with the small circle as D. We will define the point of tendency of the square with side BC as E and F. We define the point of tendency of AC with the touching point of side AC and the square is G. We define the point of tendency or the touching point of the point of tendency of the square with the circle as H. We will define the center of the small circle as O. We will define the center of the big circle as P. We define the point of tendency of side BC with the big circle as Q. We will define the point of tendency of tangent AC with the big circle as K. We define the point of tendency of tangent AC with the small circle as L. And we define the point of tendency of the small circle with the square as M. We join points O and M together by a straight line. Point O is the center of the small circle. Point M is the point of the circle itself, therefore OM is the radius of the small circle that is equal to R. That is equal, and R equals to 1 unit. So this is what is given as the equation, and we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, according to the same rule, we have the radius OD that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius PQ that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We know that all the angles inside the square are right angles, so this angle equals to 90 degrees, this angle, it is also equals to 90 degrees. This angle is equal to 90 degrees, and finally this angle is also equal to 90 degrees. And we also have here rule number 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. Side BC of triangle ABC is a side of a triangle, it is absolutely a straight line. So if we focus on the upper side of the straight line BC at point F, here the sum of the angles must be equal to 180 degrees. So which angles we have at point F? We have this angle that is equal to 90 degrees. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of BC at point F to 180 degrees. This angle must be also equal to 90 degrees. Likewise, if we focus on the upper side of BC at point E, the sum of the angles must be equal to 180 degrees, so this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees also, according to rule number 3. So actually, inside quadrilateral OMED, we have 1, 2, 3 right angles. Again, inside quadrilateral OMED, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So inside quadrilateral OED we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral OMED as a rectangle. Why? Because it has 4 right angles. Okay. So quadrilateral OMED is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, OM equals to ED. OM equals to ED. Okay, OM equals to ED according to the rule that the opposite sides of a rectangle are equal to each other. But we know that OM equals to 1, so we can write here that OM equals to 1. And from this equation, 1 equals to OM equals to ED, we will derive that ED is also equals to 1 unit. ED is equal to 1 unit. So I can write here that ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that OD equals to ME. OD equals to ME. But we know that ME, we know that OD equals to 1 unit. This is the radius of the circle, the small circle. So here, OD equals to 1 unit. And from this equation, 1 equals to OD equals to ME, we will derive that ME is also equals to 1 unit. ME is also equals to 1 unit. can write here that ME equals to 1 unit. So here we know that GE is one side of the square that is equal to 3 units. ME equals to 1 unit, therefore here GM will be equals to 3 minus 1, that is 2. So here MG equals to 2 units. So here we found out that quadrilateral MOED is not a rectangle but a square because all of its sides are equal to 1 unit. Okay, so here HG equals to 3 units, and here we have also rule number 2. According to rule number 2, the lengths of two tangents for a common external point to a circle are equal. We have here the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We actually can implement rule number 2 in our drawing. Why? Because in our drawing, if you focus on the common external point G, from the common external point G, we have two tangents to this circle, tangent GM and tangent GL. And according to rule number 2, GM equals to GL. Okay, but GM equals to 2 units, therefore GL will be equal also to 2 units. Likewise, if we focus on the common external point C, from the common external point C, we have two tangents to the small circle. Tangent, we have here tangent CL and tangent CD. Okay, and according to rule number 2, they are equal to each other. That is to say, CL equal to CD. So if we define CL as X, then CD must be also equal to X because of the fact that they are equal to each other. Okay. So here FE equals to 3 units. It is one side of the square. So in the next step, we will implement the Pythagoras theorem on the right green triangle, triangle GEC. The right green triangle, triangle GEC. By PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, according to the Pythagoras theorem. So here the hypotenuse is GC, therefore the square of the hypotenuse is GC square. That is equal to the sum of the squares of the perpendiculars, that is to say it is equal to GE square plus EC square. and repeat again, according to the Pythagoras theorem on the right, green triangle GEC, GC square equals to GE square plus EC square. Okay, so GC square, what is the value of GC? Although it is very easy to see that GC equals to 2 plus x. GC equals to 2 plus x. Therefore, GC square equals to 2 plus x square. And it is equal to GE square. G equals to 2 plus 1, that is 3. And G square is 3 squared, that is 9. Plus EC square. What is the value of EC? EC equals to 1 plus x, therefore EC square equals to 1 plus x square. So, according to equation number 1, we found out that 2 plus, here it is 2 plus x square, 2 plus x square equals to 9 plus 1 plus x square. Here we open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, 2 plus x square equals to 2 squared, that is 4, plus x square, plus 2 times 2x is 4x. And it is equal to 9 plus 1 plus x square. It is equal to 1 squared, that is 1, plus x square, plus 2x. So here we have x square on both sides of equation number 1, so x square will get cancelled. What is left from equation number 1 after we cancel x square? What is left is that in this side we have left only 4 plus 4x, that is equal. The other side we have 9 plus 1 is 10 plus 2x. So here we subtract 4 from this equation, equation number 1, and we get that 4x equals to 10 minus 4 is 6 plus 2x. So here we subtract 2x from this equation, equation number 1, and we get that according to equation number 1, 4x minus 2x is 2x. So 2x equals to 6. Here we divide this equation, equation number 1 by 2. And we get that according to equation number 1, x equals to 3 units. So we found out that x equals to 3. You can write here that x equals to 3. And also here x equals to 3. In the next step, we join points O and L together by a straight line. Point O is the center of the circle, the small circle. Point L is the point of the circle itself. Therefore, OL is the radius of the circle, that is equal to 1. In the next step, we join point C and O together by a straight line. By joining points C and O together by a straight line, we created here 2 right triangles, triangle COD and triangle COL. So in the next step, we'll prove that the 2 right triangles that we created, they can run to each other. Here we have the radius here that is 1 to the point of tendency. Therefore this angle will be equal to 90 degrees and this angle equals to 90 degrees. So those two triangles are two right triangles. So we will prove that the green small right triangle, triangle LOC, the small green right triangle, is congruent to the small green right triangle, triangle OBC. So why those right triangles can go into each other? First of all, LO equals to OD. Both the radii of the circle that is equal to 1 unit, therefore they are equal to each other. So LO equals to OD. And they are both equal to 1 unit, they are the radii of the small circle. In addition, we have already found out that CL is equals to CD. They are both equal to 3 units according to rule number 2. And finally, we have side CO that is a common side, so CO equals to itself. CO equals to CO. It's a common side that belongs to both triangles. So we actually found out that the two green small right triangles can go into each other according to side rule. Okay, so I write it down. We actually found out that the green small right triangle, triangle LOC, congruent. This is the sign of congruent to the green small right triangle, triangle ODC. According to side rule. And from the fact that the two right triangles can go into each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles will be also equal to each other. Okay, so if we define one angle as theta, then the other angle will be also equal to theta because of the fact that they are equal to each other. Okay, so both those two angles are equal to theta. So in the next step, we join points L and D together by a straight line. By joining points N and D together by a straight line, we create a triangle LDC. Actually, I found out that CO or OC is the angle bisector of angle C, this angle. So I write it down. We found out that CO is the angle bisector of angle C so you can see CO bisects angle C into two halves, each half equals to theta. Okay, in triangle LDC. I repeat again. CO is the angle bisector of angle C, triangle LDC. In the next step, we join points P and K together by a straight line. Point P is the center of the big circle. Point K is the point of the circle itself. Therefore, PK is the radius of this circle that is equal to R. In the next step, we join points P and C together by a straight line. By joining points C and P together by a straight line, we created there two big right angles. Here we have the radius PK that is drawn to the point of tendency, therefore this angle is equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. So we created here two big right angles, triangle PQC and the big right angle, triangle KPC. So actually we prove that the two big right angles can go into each other according to side also. We prove that the big right angle, triangle KPC congruent to the big right angle, triangle PQC. So, why those two big right triangles can go into each other? First of all, PK equals to PQ, they are both the radii of the circle, therefore they are equal to each other. PK is equal to PQ, they are both equal to R. In addition, if we focus on the common external point C, from the common external point C, we have two tangents to the big circle. We have tangent CK and tangent CQ. And according to rule number 2, CK is equal to CQ. CK equals to CQ according to rule number 2. And finally, PC is a common side that belongs to both triangles, so PC equals to itself as a common side that belongs to both triangles. So PC equals to PC as a common side that belongs to both triangles. So we actually proved that the two big right triangles can go into each other according to side rule. So I write it down. The big right triangle KPC can go into the big right triangle PQC according to side rule. And from the fact that the two right triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two big right triangles can go into each other, therefore repeat again, those two right triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay? As corresponding angles, they are equal to each other. So actually here we join points K and Q and K together by a straight line. We actually found here that PC is also the angle bisector of angle C in triangle KQC. So I write it down. PC is angle bisector of angle C. PC is angle bisector of this angle C. It bisects angle C into two halves. Each half equals to theta. In triangle KQC. So in conclusion, we found out that angle C has two angle bisectors. The angle bisector CO that bisects this into two halves theta and theta, and angle bisector PC that is also bisect angle C into two halves, each half equals to theta. Okay. In the next step, we'll prove that the angle by sector CO passes through point P. Repeat again, we prove that the angle by sector CO passes through point P. Okay, so our claim is that CO, that is the angle by sector of angle C, passes through this point P. Repeat again, we prove that the angle by sector CO passes through point P. We will prove our claim in a negative way. So, in a negative way, let's assume that CO doesn't pass for point P. Okay. According to our assumption, the angle by sector CO doesn't pass through point P. And from the assumption, from our wrong assumption, we will get a contradiction, and due to the contradiction, we will conclude that our assumption was wrong, and therefore CO must pass through point P. This is the process of the proof. So here, if CO doesn't pass through point P, then we will have here two angles, angle ECO. Here, the first angle is angle ECO. So according to our assumption that CO doesn't pass through point P, we will have here the first angle, that is angle ECO, that is equal to theta. Okay. Here C leg EC of this angle is part of BC. You can see it from the drawing, it is very easy to see from the drawing that CE is part of BC. CE is part of BC. That is to say, CE, leg CE and BC are located on the same straight line. Because of the fact that CE is part of VC, it is obvious that they are located on the same straight line. Okay. In the next step, we draw the second angle. The second angle is angle PCB. So this is the second angle PCB. It's already mentioned before. BC and EC are located on the same straight line. So you can put it here. Here actually CE is part of BC, therefore BC and EC are located on the same straight line. So one leg of those two angles are located on the same straight line. What about the second leg of the two angles? Here according to our assumption that CO doesn't pass through point P, it means that CO and CP are not located on the same straight line. If CO and CP will be located on the same straight line, then CO must through point P. But according to our assumption, CO doesn't pass through point P. That is to say, CO and CP are not located on the same straight line. Okay? In order that CO will be located on the same straight line as CP, CO must pass through point P. Okay? But according to our assumption, CO doesn't pass through point P, therefore CO and CP are not located on the same straight line. Okay? So we can argue that the second leg of the two angles, that it's CO and CP, are not located on the same straight line. and this conclusion is due to the fact that according to our assumption, CO doesn't pass for point P. Okay, so we have here two angles. We have here two angles that one of their leg are located on the same straight line, that is to say EC and BC are located on the same straight line, while the other leg, the second leg, are not located on the same straight line. That is to say the second leg, that is PC and OC, are not located on the same straight line. Therefore, those two angles can never be equal to each other, because they have one common leg and the second leg is not located on the same straight line. Therefore, those two angles must be different, cannot be equal to each other, must be with different sides. So if this angle is theta, this angle must be equal to alpha, and alpha is not equal to theta. Okay, so we actually found out that angle C has two different angle bisectors. That bisect it into two different halves. So angle C has two different bisectors, that is to say CO and CP, that bisect it in two different halves, while the angle bisector CO bisect angle C into two halves that are theta and theta. Angle bisector CP bisect angle C into two different halves that are alpha and alpha. And it is actually impossible. Why? Because if angle C is equal to 30 degrees, then any angle bisector of angle C will bisect it into two halves, that is 15 degrees and 15 degrees only, and not to any other halves. And here we found out that according to our assumption, angle C will be bisected into two different halves. And it is actually impossible. But if angle bisector C can be bisected only into 15 degrees and 15 degrees, if it is equal to 30 degrees, and not to any other numbers. So actually, you can write down that due to our assumption in a negative way that OC doesn't pass for point P, we arrive to a contradiction, and the contradiction is that angle C has two different angle bisectors that bisect it in two different halves. That is impossible, and because of the contradiction, we will conclude that our assumption that angle bisector and that OC doesn't pass for point P is incorrect, and therefore OC must pass for point P. Okay, I repeat on the process. In a negative way, we assume that CO doesn't pass for point P. According to this assumption, we arrived to a contradiction, and therefore we must conclude that CO must pass for point P. Okay, we finished with the proof. In the next step, we focus on the right small triangle DCO. In the right small triangle DCO, this angle equals to theta, this angle equals to 90 degrees. Therefore, the fourth angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus 90 degrees is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Okay? Likewise, we will focus on the right big triangle PQC. In the right big triangle PQC, this angle equals to theta, this angle equals to 90 degrees. Therefore, the third angle, this angle, must be equal to 90 degrees minus theta, exactly for the same reason that this angle equals to 90 degrees minus theta. Okay, so in the next step, we'll prove that those two triangles are similar to each other. So we'll prove that the right big triangle PQC is similar to the right green small triangle, triangle ODC. So why those two triangles are similar to each other? First of all, we just right now found out that those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we can write down that angle QPC in the big right triangle is equal to this angle, that is actually angle DOC, repeat again, angle QPC equals to angle DOC equals to 90 degrees minus theta. So both angles are equal to 90 degrees minus theta, therefore they are equal to each other. In addition, we have those two angles that they are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle PQC in the big right triangle, and it is equal to this angle, this is actually angle ODC. Repeat again, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle, angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. Okay, so we can write down that we will define angle theta in two different names. Angle theta equals to angle PCQ, and it equals to itself. Angle theta can be also called angle OCD. Repeat again, angle theta equals to itself. This is the meaning of this line. We call angle theta two different names, so angle theta equals to itself as a common angle that belongs to both triangles. So we actually proved that the big right triangle PQC is similar to the small green right triangle ODC according to angle similarity rule. So I write it down. The big angle and the big triangle PQC is similar. This is the sign of similar to the small right green triangle ODC according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PQ in the big right triangle over OD in the small green right triangle is equal to QC in the big right triangle over DC in the small green right triangle. Repeat again. From the fact that the two right triangles are similar to each other, we conclude that PQ over OD equals to QC over DC. PQ equals to R, it is the radius of the big circle. OD is the radius of the small circle that is equal to 1, and it is equal to QC. What is the value of QC? The value of QC equals to 3 plus 1 plus 3 is 7. So it is 7 plus QF. 7 plus QF. So we substitute QC by 7 plus QF. Over DC. Here DC equals to X, that is equal to 3 units. So we substitute DC by 3. In conclusion, we found out that according to equation number 1, R equals to 7 plus QF over 3. Here we will multiply this equation number 1 by 3, and we will get that according to equation number 1, R equals to QF plus 7. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, QF equals to 3R minus 7. So I found out that according to equation number 1, QF equals to 3R minus 7. So I write in the drawing that QF equals to 3R minus 7. QF equals to 3R minus 7. So, because of the fact that the side length of this square is equal to 3 units, we will examine 3 cases for the value of the radius of the big circle, that is capital R. Capital R could be less than 3 units. This will be the first case. According to the second case, capital R equals exactly to 3 units. And according to the third case, capital R will be greater than 3 units. We will examine each case in order to find out which case is suitable for our drawing. Okay, so as I already mentioned, the first case is the case that R is less than 3 units. So I write it down. So case 1, if R or if capital R is less than 3 units. So if capital R is less than 3 units, then we will have a circle that its radius is less than 3 units. So I will draw a circle with a radius that is less than 3 units. The side length of the square is 3 units, so it will be higher than the radius that is less than 3 units. So here you can see in the drawing the side length of the square is higher than the radius. Here we have the radius that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, according to rule number 1, of course. So here we have we define the point of tendency of tangent edge F with the radius as point X, so inside quadrilateral PXQF, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So, inside quadrilateral PXQF, we have 4 right angles. Therefore, quadrilateral PXQF, this quadrilateral, is a rectangle. Quadrilateral PXQF is a rectangle. Why? Because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side PX must be equal to side QF. Okay? But here, side PX is the radius of the circle that is equal to R. So, here, from this equation, R equals to Px equals to Qf, we derive that R equals to Qf. R equals to Qf. From one side, R equals to Qf. But from the other side, we have already found out that Qf equals to 3R minus 7. So you can write here that Qf equals to 3R minus 7. And from this equation, R equals to Qf equals to 3R minus 7, we derive that R equals to 3R minus 7. Here we subtract R from this equation and we get that 0 equals to 3R minus R is 2R minus 7. Here we add 7 to this equation and we get that 7 equals to 2R. Here we divide this equation by 2 and we get that R equals to 3.5 units. R equals to 3.5 units. For one side, but according to our assumption, R is less than 3 units. And it is a contradiction. R cannot be both less than 3 units and also equals to 3.5 units. Okay, here we have a contradiction. R cannot be both less than 3 units and also equal to 3.5 units. So due to the contradiction, we conclude that R cannot be less than 3 units. Why? Because we have a contradiction here. Okay? So we have also the second case that R equals to 3 units. So according to the second case, the radius of the big circle is equal exactly to 3 units. This is case 2. If R equals to 3 units, so then we have the radius, we know that the radius of the big circle is equal exactly to 3 units. So I will draw a radius that is exactly equals to 3 units. Okay. We know also that the side length of the square is also equals to 3 units. Here, according to rule number 1, we have the radius PL that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees. So actually inside quadrilateral PLQF we have 1, 2, 3 right angles. I'll repeat again, inside this quadrilateral we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. So actually inside quadrilateral PLQF we have 4 right angles. Therefore quadrilateral PLQF is a rectangle. Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle PLQF are equal to each other. Therefore, PL is equal to QF. Okay, PL equals to QF. But we know that PL is the radius of the circle that is equal to 3 units according to our assumption. PL equals to 3 units. So from this equation 3 equals to PL equals to QF, we will derive that QF is also equals to 3 units. QF equals to 3 units. So from one side QF equals to 3 units. From the other side we have already found out that QF equals to 3R minus 7. And from this equation 3R minus 7 equals to QF equals to 3, we will derive that 3R minus 7 equals to 3. Here we add 7 to this equation and we get that 3R equals to 3 plus 7 is 10. Here we divide this equation by 3 and we get that the radius of the big circle equals to 3 and a third units, while according to our assumption R equals to 3. So we have here a contradiction. R cannot be simultaneously equals to 3 units and also will be equal to 3 and a third units. So due to the contradiction, we'll conclude that R cannot be equal to 3 units. Therefore, only the third case is left. According to the first case, R is greater than 3 units. Case 3 is that R is greater than 3 units. So we have a circle with a radius that is greater than 3 units, so I draw the circle. Because of the fact that the radius is greater than 3 units, it means that the radius will be higher than the square. That is, that the side length of it is equal to 3 units. So here the radius, the side length of the square is shorter than the radius. Okay. So we'll do a construction here from point L. We'll draw perpendicular QF, the radius QF. I repeat again, from point L, this point, we will draw perpendicular on the radius QP. The radius QP, so here, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point L and the radius PQ as T. So inside quadrilateral PLQF, this quadrilateral, we have 1, 2, 3 right angles. 1, 2, 3 right angles. Therefore, the third angle must be also equal to 90 degrees. So this angle equals to 90 degrees. Therefore, inside quadrilateral TLQF, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral TLQF as a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side TL of the rectangle must be equal to side QF of the rectangle. TL equals to QF, but we already found out that QF equals to 3r minus 7. So we can write here that QF equals to 3r minus 7. And from this equation, TL equals to QF equals to 3r minus 7. We will derive that TL is also equals to 3r minus 7. Okay, here. TL is also equals to 3r minus 7. What is the length of line segment TP or PT? PT, it is very easy to see from the drawing that PT is equal to PQ minus TQ. Again, PT equals to PQ minus TQ. It is equal to PQ minus TQ. Okay, so PT equals to PQ. PQ is the radius of this big circle that is equal to R minus TQ. What is the value of TQ? So the opposite sides of rectangle TLPQ are equal to each other. That is to say, TQ is equal to LF. TQ equals to LF. According to the rule that the opposite sides of a rectangle are equal to each other. But LF equals to 3, it is one side of the square. LF equals to 3, and from this equation TQ equals to LF equals to 3, we will derive that TQ is equal to 3 units. TQ equals to 3 units. So here we have the equation that PT equals to R minus TQ. That is to say, PT equals to R minus TQ, and we just right now found out that TQ equals to 3 units. So here we substitute TQ by 3 and we get that PT equals to R minus 3. Here PT equals to R minus 3. Here we join points P and M together by a straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that is equal to R. In the next step, we'll implement the Pythagoras theorem on the right green triangle, triangle PTL. So I'll copy triangle PTL in a new page and we'll implement the Pythagoras theorem on this triangle. So here triangle PTQ. Side PT equals to R minus 3. Side TQ equals to 3R minus 7. And the hypotenuse PL, the short triangle PTL. This triangle PTL. The green right triangle is triangle PTL. Okay. So the hypotenuse PL is equal to R. So actually, this is the right triangle, triangle PTL, that I copied from the original drawing. So here, according to the Pythagoras theorem, on the right triangle, triangle PTL, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, we get that PL square equals to PT square plus TL square. Again, PL square equals to PT square plus TL square. I write it down. Here, by PT, we get that PL square equals to PT square plus PL square. So here PL equals to R, therefore PL square is R square plus PT square. PT equals to R minus 3, therefore PT square is R minus 3 square plus TL square. TL equals to 3R minus 7, therefore TL square is 3R minus 7 square. So here we will open the brackets on this side of equation number 1, and we get that according to equation number 1, R square equals to R minus 3 square. R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3R minus 7 square. 3R minus 7 square equals to 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, and minus 6R times 7 is minus 42R. So here we have R square on both sides of equation number 1, so R square will get cancelled. So it is left from equation number 1 after we cancel R square. In this side of the equation, nothing is left, so we have 0. That is equal to 9 plus 49 is 58, plus 9R square minus 6r minus 42r is minus 48r. So we have here a quadratic equation. According to the quadratic equation, 9r squared minus 48r plus 58 is equal to 0. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of the quadratic equation and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, the coefficient a is equal to 9, the coefficient b is equal to minus 48, and finally the coefficient c is equal to 58. And the variable that we are looking for in our specific quadratic equation is r, so x equals to r. So we put the data inside the formula for x and we find out the value of the values of r, because r equals to x. So r equals to minus b, b equals to minus 48, therefore minus b is minus 48, that is plus 48, plus minus square root of b squared. B is minus 48, so b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 36, and minus 36 times 58 is 2088 over 2a. A is 9, so 2a is 18. Okay. So we found out that r equals to 48 plus minus 2304 minus 2088 is 216. So inside the root we left only 216 over 18. And the square root of 216 is 14.6969. So here we'll have two solutions that are possible for r. The first solution for r is that r equals to 48 minus 14.6969 over 18. So r equals to 48 minus 14.6969 is 33.3031 over 18. So 33.3031 over 18 is 1.85. So I found out that the radius of the big circle equals to 1.85, but because of the fact that we have already found out that r cannot be less than 3 units and 1.85 is less than 3 units, therefore here r cannot be less than 3 units. Therefore, r cannot be equal to 1.85, that is less than 3 units. We cancel this solution, we left only in the second solution, that are equals to 48 plus 14.6969 over 18. So 48 plus 14.6969 is equal to 62.6969 over 18. 62.6969 over 18 equals to 3.483 units. So I found out that the radius of the big circle is equal to 4.483 units. That is actually greater than 3 units. Therefore, it is absolutely a possible solution according to analysis. R absolutely can be greater than 3 units. It is the first case that is allowable. We didn't find any contradiction in the third case that R is greater than 3 units. So we found out that the radius of this big circle is equal to 3.483 units. Okay, in the next step I'll summarize the lecture. So in the drawing we have a big triangle. Inside the big triangle we have 2 circles and a square. We know that the side length of the square is equal to 3 units, and the radius of this small circle is equal to 1 unit, and our mission is to find out the radius of the big circle. Okay, so first of all, in this lecture we used 3 rules in order to find out the radius of this big circle. So I present to you again the 3 rules that we used in this question. We have rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. We have here tangent AB, that is tangent to the circle, and at this point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So this is number 1. Then I presented to you rule number 2. According to rule number 2, the lengths of 2 tangents from a common external point to a circle are equal. Here we have the common external point P, and from the common external point P, we have 2 tangents to this circle. We have tangent PA and tangent PB, and according to this rule number 3 and rule number 2, PA is equal to PB. And then I presented to you rule number 3. We used rule number 3 a lot in other question. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So we have the straight line CD, if we focus on the upper side of the straight line CD 8.0, we know that here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have angle alpha and angle beta, and the sum of those two angles must be equal to 180 degrees. That is to say, alpha plus beta must be equal to 180 degrees. Okay. So here we arrive to this formula by using the three rules. Then, if we focus on quadrilateral MOED, we actually use the three rules in order to conclude that this quadrilateral is a rectangle. Why? Because it has four right angles. According to the three rules that I presented, this quadrilateral has four right angles, and therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OM equals to ED. OM equals to ED. But we know that OM equals to 1 unit. It is the radius of the small circle. So we can write here that OM equals to 1, and for this equation 1 equals to OM equals to ED, we will derive that ED is also equals to 1 unit. And likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that MOD equals to ME. OD equals to ME. But we know that OD equals to 1 unit. It is the radius of the circle. And for this equation, 1 equals to OD equals to ME, we derive that ME is also equals to 1 unit. So we actually found out that quadrilateral OMED is not a rectangle, but a square. Because all of its sides are equal to each other. Then use the rule number 2. If we focus on the common external point G, for the common external point G, we have two tangents to this circle, tangent GL and tangent GM. And according to rule number 2, GL equals to GM. And what is the value of GL? GL equals to GE, that is 3, minus ME, that is 1. 3 minus 1 is 2. So GM equals to GL and GM equals to 2, therefore GL will be also equal to 2. Likewise, we focused on the common external point C. From the common external point C, we have two tangents to this circle. We have tangent GL and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CL equals to CD. So if CL equals to X, then it means that CD must be also equal to X because of the fact that they are equal to each other. Then we implemented the Pythagoras theorem on this right green triangle, triangle GEC. According to the Pythagoras theorem on this right green triangle, GC square equals to GE square plus ED square. Repeat again. In the right green triangle, triangle GEC, GC square equals to GE square plus EC square. Okay. GC, what is the value of GC? It is very easy to see from the drawing that GC equals to 2 plus X. Okay. Is equal to 2 plus X, so GC square is 2 plus X squared plus GE. GE is 2 plus 1, that is 3, therefore GE square will be equal to 3 squared, that is 9, plus EC square. EC equals to 1 plus X. EC equals to 1 plus X, therefore EC square is 1 plus X squared. So in conclusion, according to equation number 1, we found out that 2 plus X squared equals to 9 plus X squared. Here we open the brackets of both sides of equation number 1, and we found out that according to equation number 1, 2 plus X squared equals to 2 squared, that is 4, plus X squared, plus 2 times 2X, that is 4X. And it is equal to 9 plus 1 plus X squared. 1 plus X squared equals to 1 squared, that is 1, plus x squared plus 2x. Okay, here we have x squared both sides of equation number 1, so x squared will get cancelled. So after we cancel x squared, we left only with this side of the equation with 4 plus 4x. And the other side of the equation we have 9 plus 1, that is 10, plus 2x. So we subtracted 4 from this equation number 1, and found out that according to equation number 1, 4x equals to 10 minus 4 is 6, plus 2x. Here we subtracted 2x from this equation number 1, and we found out that according to equation number 1, 4x minus 2x is 2x, so 2x equals to 6. Here we divided this equation number 1 by 2, and we got that x equals to 6 over 2, that is 3. So x equals to 3 units. You can write here that x equals to 3 and x equals to 3. Then we joined points O and L together by a straight line. Point O is the center of the circle. Point L is the point of the circle itself. Therefore, LO is the radius of the circle, that is equal to 1. Then we joined point C and O together by a straight line. And we created here two right triangles, triangle CLO and triangle CDO. We proved that those two right triangles can go into each other according to side rule. When they can go into each other, first of all, LO equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, CL equals to CD equals to 3 units according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself. So we found out that those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if one angle is equal to theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay, then we joined points L and D together by a straight line and created here triangle ADC. We can conclude from what we did until now that CO is the angle bisector of angle C. Again, CO is the angle bisector of angle C because it bisects angle C into two halves. Each half equals to theta. So I can write down that CO is the angle bisector of angle C in triangle LDC. Okay, then we joined points P and K together by a straight line. Point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the circle, that is equal to 1. Then we joined points P and C together by a straight line, and this way created two big right triangles. Those two triangles can go into each other according to side rule. Why? Because PK equals to PQ, they are both the radii of the circle, therefore they are equal to each other. In addition, if we focus on point C, from the common standpoint point C, we have two tangents to the big circle, tangent CK and tangent CQ, and according to rule number 2, they are equal to each other. That is to say, CK equals to CQ, and finally, CP or PC is the common side that belongs to both triangles, so CP equals to itself as the common side. So we found out that those two triangles can go into each other according to side rule, and from the fact that they can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is equal to theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So I actually found we joined points K and Q together by a straight line, and this way we created triangle KQC. So according to what we did until now, we can conclude that PC is also the angle bisector of angle C in triangle KQC. Triangle KQC. Here, PC bisects angle C into two halves. Each half equals to theta. So In conclusion, we found out that this angle C, is two angle bisector, and two angle bisectors. Angle bisector CO and angle bisector CP. Okay, they both bisect angle C into two halves, each half equals to theta. Okay, and then we had a claim. According to our claim, CO passes through point P. Again, the angle bisector CO passes through point P. Or in other words, according to our claim, point C, O, and P, they are all located on the same straight line. I'll repeat on the claim. According to our claim, CO passes through point P. CO passes through point P. And we proved our claim in a negative way. That is to say, let's assume that CO doesn't pass through point P. So according to our assumption, CO doesn't pass through point P. And then we arrive to a contradiction. Due to the contradiction, we concluded that our assumption is incorrect. Therefore, we must conclude that CO does pass. Indeed, it passes from point P. That's just the proof. So according to assumption, CO doesn't pass from point P. Therefore, we will have here two angles, angle OCE, that is equal to theta. It's very easy to see that CE, leg CE of this angle is part of CB. Leg CE is part of CB. So if leg CE of the angle is part of CB, it means that CE and CB, they are both located on the same straight line. Okay? So we can write down that here CE and CB or BC, they are both located on the same straight line because of the fact that CE is part of CB. And then I draw the second leg, that is the second angle, that is angle PCB. This is angle PCB. So I copied angle PCB here, and here again you can see that CE is part of CB, therefore CE and BC, they are both located on the same straight line. And what about the second leg of those two angles? Here we have leg CO, and the second leg here is angle C, and is leg CP. According to our assumption, CO doesn't pass through point P. If CO doesn't pass through point P, it means that CO and CP are not located on the same straight line. Okay? Here we can also, here CO, we can write here CP, we have angle leg CP, okay? In leg CP, here CP will be here we can write down point E, so CEP can be one straight line only if CO, here we will have this will be point O. Okay, so here you can see that CO, if CO doesn't pass from point P, it means that points C, O, and P are not located on the same straight line. Therefore, CO and CP are not located on the same straight line because of the fact that CO doesn't pass for point P. So we have one leg that is a common leg, and the second leg of the two angles is a different leg. Therefore, those two angles can never be equal to each other. Because in order that those two angles will be equal to each other, both legs must be located on the same straight line. But according to our assumption, the second leg of those two angles are not located on the same straight line because CO doesn't pass for point P. Okay, COP will be one straight line only if CO passes for point P. Otherwise, it is not one straight line. Therefore, CP and CO will be located on different straight lines. Therefore, we will get two different angles. They can be equal, those two angles can be equal to each other only if CO passes from point P. Otherwise, there will be different angles. So, if this angle is theta, then this angle will be equal to alpha according to our assumption. So, we actually found out that angle C has two different angle bisectors, CO and CP, that bisects it into two different halves. While angle bisector CO bisects it into two halves that are theta and theta, angle bisector CP bisects it into different two halves that are alpha and alpha. And it is impossible. Why? Because if angle theta is equal to, if angle C is equal to 30 degrees, then any angle bisector will bisect it only to 15 degrees and 15 degrees, and not to any other two halves. Okay? So, due to the contradiction, we conclude that our assumption that angle that the CO doesn't pass for point P is incorrect assumption. Therefore, we conclude that CO must pass for point P. Okay, and then we define in triangle ODC. This angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. For the same reason, in triangle PQC, this angle must be also equal to 90 degrees minus theta. We proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that the two triangles can go to each other, are similar to each other, we will conclude that PQ over OD equals to QC over DC. PQ equals to R, OD equals to 1, QC equals to 7 plus QE, DC equals to 3. And from this equation we have concluded that QF equals to 3R minus 7. Okay, so here we will have three different possibilities for the value of R. R could be less than 3 units, R could be equal to 3 units, and R could be greater than 3 units. In the two first cases, we got a contradiction, therefore we have only the third case that is last, that is remains, that R is greater than 3 units. So if R is greater than 3 units, then we will get this drawing. From this drawing, I copied the right triangle PTL in a new page and implemented the Pythagoras theorem on this right triangle, and we got that r squared equals to 1 3 squared plus 3r 1 7 squared. We solved this equation. This is a quadratic equation. We got two solutions. The first solution is that r equals to 1.85 units, but according to our analysis, r cannot be less than 3 units, and r that is equal to 1.85 units, it is less than 3 units, therefore we left only with the second solution, and according to the second solution, the radius of this circle, it is equal to 3.483 units. Okay, thank you very much.